So now let's see how we solve that specific problem, both, or at least mathematically. How can we solve, or try to solve this problem in terms of mathematics? So, in fact, we have a partial differential equation problem defined on a body, which is our continuum mechanics body, which has a reference configuration at the time of references, of reference time, t0 equals 0, and a long time due to some actions, typically the body forces, characterized by this vector, which is the specific body forces vector, a data of the problem. We have also some tractions, which are applied with the same portion of the boundary of the body, dv, which again is a function of the space and time, which is known. Of course, they take initially some values, but they, in principle, in the more general case, they can evolve. So these are the actions. Then we assume that the material inside the body is endowed with the elastic constitutive equations, okay, the ones that we have visited. We have also that we have some part of the boundary where we have some prescription of the displacements. We go now in deep with that issue, and some part we have prescribed some attractions. We also assume a small strains theory or infinitesimal displays theory, so we do not distinguish between the reference configuration and the present configurations, because at real scale they are little separated from each other. And that is the problem we have to solve. We have to solve a first partial differential equation in space and time. Look that there are derivatives with respect to time. There are derivatives with respect to space, this gradient. These are three equations which we term the Cauchy's equations of motion, which are nothing else than the mathematical expression of the principle of linear momentum balance. That is the first part of the second Newton's law. How many equations are there here? Three. Okay, these three. We can just check that this is a vector with three components. So this is a vector with three components. So there are three equations here. Then we have the constitutive equation, the one that we have considered for an isotropic linear elastic material. The stresses and the strains are related linearly, proportionally, so double strain means double stresses, and so on. And through two properties, two coefficients that are the Lamé coefficients, lambda mu, which have to be identified by every of these elastic material. So they are different if we talk about concrete or we deal about steel. So how many equations are here? Six, because this is a tensor that have 9 components, but we always assume from now on, or from sometimes since some time ago, that the symmetry of the stress tensor reduces the number to 6. So we have 6 equations here, 3 plus 6, 9. And also we have the kinematical compatibility equations that we call the geometrical equation, which says that the strains are related to the displacements to that partial differential equations, that are derivative with respect to space here, epsilon equal the symmetric gradient of u, which is that way. How many equations are here? 6. So 6 plus 6, 12 plus 15 equations. How many unknowns are involved? Look, we have the displacement field, which is a vector in the general case, which imposes 3 components, the unknowns. The strain field, which appears here, which is it's a tensor, a symmetric tensor, so involves 6 unknowns, and the stresses, which is a symmetric tensor also involving 6 unknowns. So we have 6 unknowns and 6 equations. Look, the density here is specified with 0 value, meaning that this is a data, that is the initial density, okay, as we also have studied. So from the mathematical point of view, we have to determine functions which are functions of a space and time. So a space is the Euclidean space which corresponds to R3. That means the three components can be moved, all the solutions in a space can move in the real space, positive and negative, so R3. Times, that means that time also moves in R positive. That means the values, the positive values of R. Because time, if we start at time 0, then we can proceed along time but not before 0. Okay? So time moves at some interval at the positive real domain. Okay, so this is the final, the differential equations, and as you know, any differential equations, when integrated, will produce some constants which have to be determined through boundary conditions. Okay, whenever we integrate a differential, there appear some constants, and they have to appear with boundary conditions. What are the boundary conditions in that case? Well, there are two types of boundary conditions. In a space, so boundary conditions in terms of what happens of these unknowns, or some of these unknowns, at certain points of the space, and in time, boundary conditions that says what happens when we are at the boundary of these. So, for instance, at the initial time, which is the boundary of where this time lives, the interval of time lives. So, what are these equations? Look, we have any body, for instance, that one. If I just leave it, the boundary moves, okay? But in general, we have some boundary conditions. Now I'm holding this bottle on my hand, so I'm posing some displacements to be 0 or to move in a certain way, right? So there is a part of the boundary, not all the boundary, just a part where I am just putting placing my fingers to impose the displacements. There is one part of the boundary where displacements are known and imposed. We'll denote this part of the boundary gamma u. So the boundary of the body now will be denoted by gamma, and will be split in one part of the boundary where the displacements are known. For instance, the part where I impose that displacements from here to here, for instance, in those points I know how the displacements are because I impose them. Okay, there could be other places or other parts of the boundary where I know where the tractions, what the tractions are. For instance, if I just consider that point, if I just put some forces here, some forces, not imposing displacement, some forces here, at the points where I place the forces, I know the most general way of expressing the forces at the boundary is the traction vector, the force per unit of stress. So there are another part of the boundary where I know the forces. This part can be that corresponding to 0 forces. For instance, in that case, on these points, all these points here, there is no force applied. Okay, so this is points corresponding where the tractions are known. How much are the tractions? The tractions, which is that vector. How much is the tractions at that point? 0. At that point, 0. At the point, 0. If I put a force here, the tractions at the point are different from 0. But I assume that I know them. Okay? Look, and finally, there could be points of the boundary with mixed conditions for that. We'll see that in specifically. So, finally, the boundary is split into 3 parts. The boundary of V, expressed in that way, which now is term gamma, is considered the union of gamma u, where we have displacements known, gamma sigma, where we have tractions known, and gamma u sigma, where we have some components of the displacements known and some components of the forces known. Okay? And that's important. This defines all points of boundary. So the union of these 3 is gamma. So that means that in a boundary, either we know the displacements, so the point corresponds to this boundary, or we know the forces applied, the tractions, or we know both, some components of one and some component of the other. But there are not more points at the boundary. That's all. So the union of these three boundaries is the boundary of the body. And also, those boundaries are disjoint in the sense that, of course, simultaneously we cannot have prescribed all displacements, all component displacements, and all component of forces. So we have for a given component or even point, we have either the displacements prescribed or the forces, the tractions prescribed, not both simultaneously. So you will see that in short in an example. So in general, in gamma u, we have the prescription that the displacements are equal to some value u star, which is known. That's something that we know. That can be varying a long time, but it's known. Okay, that's the data. So that's the component, the equation in the format of the general description, and this is a component description of the equation. So about the tractions, what do you know? If we know the tractions at these points of the boundary gamma sigma, then in virtue of the Cauchy's equation, the Cauchy's lemma, sigma times n is equal to t. So at that point, we can impose the condition that some of the unknowns, sigma, are not free to vary because sigma times the normal, we know the normal, always the outward normal, have to be equal to this prescribed tractions t. So this establishes three conditions at every point of gamma u, a gamma sigma, that are expressed in initial form in that, in compact form in that form. So sigma j times mj, return, that's the component I, component I of t for I equal 1, 2, 3. Okay, and then there could be points like that, but some components have displacements prescribed and some components have traction prescribed. So let's see that in a typical structural analysis example. You are familiar with that. So let's consider this beam. This is a clamped and support beam. The beam is clamped at this point, at this end. So all displacements are prescribed and it's supported at this plane. Let's consider the 2D cases. So you just look in that dimension and that direction. So what happened with this surface here? Here we know that the displacement x is 0 and the displacement y is 0. That is what we say when we have a clamp, un empotramiento. What happens, so that's its domain gamma u. What happened at this upper face? Imagine that you have a distributed load P. So we know that the traction vector at this point is known. The x component is 0 because forces are vertical. The y component is minus P. Okay, we know that. What happens at this end here, this side here? Well, this is the same, excepting that the force P is 0. So now we know that the component x is 0, the component y is 0. So that's gamma sigma. These and these are gamma sigma boundaries. This also is a gamma sigma boundary, the lower phase, because here also there is no force applied, so Tx equals 0, Ty equals 0. And what about that? This is a simple support. So we know that here, due to this prescription, the vertical displacements are 0. So Uy equals 0. But also due to this type of a sliding support, we know that the horizontal forces are 0. So the component x has a force prescription and the component y has a displacement prescription. So this is typically a gamma UC. Okay? But look that with that we have defined all the boundaries. In all the boundaries, we have either, for every specific component, we have either the component prescribed in terms of displacements or the component prescribed in terms of forces. And all points are prescribed this way. So we'll consider that we have domains gamma u, where displacements are prescribed, like this, and domains gamma sigma, where forces are prescribed. That meaning that could be domains where there are some components where prescription is enforced and some components where prescriptions are in displacement. But the point is that all points of the boundary have some prescription, one, and second, the prescription is, for a given component, the prescription is either in displacements or in forces, not in both. Not in both. Okay? So these are the conditions that we have to apply, and you will see that when we do solve problems of that, we will look and we will apply these conditions. These are conditions in the space. Whenever we have time, then we apply also some conditions in time. So in the interval, at the beginning of the interval of interest, we know that the displacements are zero, because displacements naturally are defined as the relative position of a particle with respect to its position at the reference configuration. Since at the reference configuration both are the same, so displacements are zero. So that is a natural condition and in time. So when you place here in all that, in these equations, when you place time equals zero, then it has to return u equals zero. Okay? And in consequence also, the stresses are zero and the strains is zero. But these are rather a consequence than imposition. And the second condition that we'll have is the initial velocity. In general, we have that known what is the velocity. What is the velocity? The displacement, the derivative with respect to time of the position, which is the same than the derivative with respect to time of displacements. And that is called u dot, it's denoted by u dot, or it's the velocity. The velocity when specified at time equals zero is something that in general is supposed to be known. Okay? So for instance, if I move that body, assuming it's an elastic body, if the problem involves time, then for instance I give him a certain velocity and I just leave it after the time. If time starts counting at the point that this body arrives to that, when I do that, at this time there is initial velocity which is supposed to know. And then let it go and compute the velocity and all other displacements at the rest of the time. Okay? So these are the boundary conditions, and with that it can be proven that we have enough boundary conditions to find a solution of, don't forget, that boundary partial differential equation system, which implies integrating that, obtaining constants, and solving constants with the help of these boundary conditions. Okay, so that's the theory. We have this system of equations, these boundary conditions in a space. Look, I've just considered u and sigma. There is always implicitly considered u sigma boundaries here, and initial conditions in time. Okay? So, in principle, we shall look at this problem as a sort of machine of solving the problem, as machinery. So we have some data. What are the data? What do we know in advance of the problem? We know the specific body forces. For instance, in our case, most of cases, what is this due to? Weight, gravity actions. This one. These are the forces that we have at the boundary of the problem. For instance, if I consider this desk, if I just place some force on this surface, I know that. I could place at this point some forces, greater, some horizontal, some vertical, etc. So these also are known. The imposed displacements. Of course, we know what part of the boundary is supported or where you impose a displacement. The example like that, if I impose to this body that displacement, so at this part here where I have my fingers, we have displacement which are zero, and at that part here where I have my right hand side fingers, then I have displacement which I know is imposed. It's different if I put that displacement, if I put that displacement. That's the data of the problem. And then I also know what is the initial velocity in the case of the problems I mentioned you. So these are considered actions. These actions, in general, they can be constant, but they can change in a long time. So, for instance, actions, for instance, that displacement I impose here, can vary at the time. I can impose some time varying variation of displacements. I can also put some varying forces. I could also put some initial velocities, etc. So in general, these actions, this set of actions that is data that I know before the analysis are called, denoted as A, as a function of space and time. So then I have a mathematical model. What is the mathematical model? This. The boundary, so the partial differential equations and the boundary conditions. Imagine that I have a machine that when I introduce to this problem some actions, it solves the problem and returns the responses. What are the responses? The 3 plus 6 plus 6 equations that I want to know, every one, the mechanical actions, displacements as function of a space. I want to know displacements at every point of the space, at every time of the analysis, the strains and the stresses, these are the responses. If I change the actions, I will obtain, without changing the mathematical model are these equations. It doesn't change. But then I will obtain some different equations. So it's like a machinery that with some feeding data, I obtain some answer, which are the displacement, the stresses, and the strains. Those entities that I need as an engineer to take decisions about the problem. Okay? Look that I said that in general actions depend on time. But there are problems in which time, although present there, because time is present everything in our problems, doesn't play any mathematical role. That is what we call quasi-static problem. So when time does play a mathematical role, the general problem, the general case, it's the dynamic problem, but as I say, that some cases in which for mathematical purposes we can forget that the solution lives a long time, the problem is set quasi-static. That is important.